Hi, I'm Wenjie Zheng. I'm happy to be here to present our work in KAI 2020, a skin stroke display on the eye ring through head-mounted displays. This work was in collaboration with Yizhen and Li Wei from National Jiao Tong University and Roshan from Rochester Institute of Technology. The skin stroke display is a tactile display which can create stroke haptic feedback on the skin region around your eye by motorized agent. So our motivation is that VR HMDs offer a unique opportunity to explore haptic feedback on face, like thermal, vibrotactile, or combining several haptic modules. However, the space for installing these actuators is limited inside an HMD, so the haptic outputs are often discrete. Skin drag displays allow the high density and continuous cues through dragging a tactor on the user's skin, for example, wrist or finger. So we apply the concept of skin drag to create dense and continuous cues on the eye ring through a motorized agent inside the HMD. Since there is no physical tactor for skin stretching, we name our feedback as skin stroke. So our prototype is mounted on the lens of VR headsets, and each of them has a nozzle moving around the eye and exerting air jet to produce point or stroke tactile feedback on the eye ring. So here I will show our system design. To rotate the nozzle around the eye, we use DC motor to rotate the drive gear and drives blow gear. The PTFE tube connects the air pump to the nozzle and it is embedded inside the gap of blow gear. And we use track wall and base to constrain all the components. And this is our prototype. To control the movement of the nozzle, we use IR sensor and encoder disc. And also to prevent the air jet blowing into eyes directly, we modify the nozzle so that it was tilting 10 degrees outward. And I will talk about this part later on. So our actual moving range of the nozzle is 330 degrees because of the mounting position of IR sensor. And the airflow passes through the PDF tube, and the nozzle then becomes air jet to create tactile sensation on the eye ring. And to control the air jet, we use PWM signal to drive two air pumps, and each of them connects to the left and the right nozzle respectively. So here I will show the stroking region, the actual stroking region in our system. So first of all, we set the lens to eyes distance to 10 millimeters. And here the green circle shows the restricted region of air jets between the open of eyelids. And here we have two assumptions about our air jet. The first one is we make our nozzle tilting 10 degrees outward, and we assume the angle of turbulent air jet is 24 degrees from side to side. And with the black ring representing the traveling distance of the aperture of the nozzle, we can obtain the expected stroking region of our system, which is the blue ring. So we can make sure that our system will not exert air jets into eyes directly. And we create 4 applications for our system, including 2 off-screen indicators, an expert interface and a natural mapping, and tactile I/O progress display, and simulating feedback around the eyes. So in the expert interface, we map the front and rear tactile displays to the front off-screen region and rear off-screen region, so that the users, to indicate users where the off-screen enemies are coming from. And in the natural mapping, we use the left side on the left ring and the right side on the right ring to indicate the off-screen objects in a 360 video. So here, as a user finishes the Uranus, our system indicates the next planet in the 360 video, which is Neptune. Then, after he finished that, we will indicate the planets again, and he can find the Pluto on his right-hand side. And in the tactile I/O progress display, we use the skin stroke beneath the eye as a progress bar for watching video. And we also collocate two ring-shaped touch bars on the HMD that completes a tactile I/O interaction loop for direct control. So here you can see the lower part displays represent a timeline. And once you touch the input interface, the video will go back to the touched time point. And we also simulate the tactile feedback of activities around the eye. For example, when watching a makeup video, users can feel tactile feedback of the makeup on the avatar, like blending out beneath the eye and putting on nose shadow by exerting strokes near the side of the nose. And also, we use continuous strokes to simulate the highlighting feedback on your cheek. So we conduct 3 user studies. The first and the second study determine standard intensity and equal sensation feedback around the eye. Then we apply feedback to conduct a target recognition test on the eye ring. So in study 1, we want to find a suitable intensity around the eyes. For the setup, we constrain the HMD by bracket and key retractors to reduce the weight and restrict head direction. We also cut off a part of fast cushion to minimize the interference against air jet. We use 2 down, 1 up staircase method to find absolute detection threshold of 8 locations on both eye rings. And the estimated threshold was the average of last 4 reversal points. And here are our results. And you can see the mean thresholds distributed between 2 to 4 m-bar on the plot. And we also found that the sensitivity of location 4 was significantly lower than others. And our participants reported that it's easier to perceive air jet on location 0 and 7 because of the hair of eyebrows. And they also reported that they detected turbulent airflow going into eyes on location 2 and 3. So the turbulent airflow is because that airflow blowing into eyes that reflects on the tilted human face. So we measure the upper bound threshold on location 2 and 3 on the right eye, and participants, they have to answer whether an air jet was uncomfortable following the procedure in ADT. So result shows that participants could tolerate a stronger air jet on location 3 compared to location 2. And now we can determine a standard intensity that is detectable and not causing discomfort. And therefore, we pick 8 m-bar on location 2 to avoid blurred sensation and enhance the acuity of air jet. And next, we want to adjust the feedback on 8 directions to have equal sensation as the standard intensity on location 2. So we ask participants to compare the standard intensity on location 2 and other 7 locations. They have to adjust the intensity and repeat until they felt 2 stimuli were equal. So here are the results. We apply these adjust intensities to a region of 45 degrees around each direction for the further study. And we also found that participants reported itchiness on location 5 and 7. And in the last study, we investigate how well could users recognize our feedback when doing a primary task. We compared 3 stimulus types and inducing cognitive load. We would like to know whether participants can recognize our feedback when doing a task. So we induce cognitive load by Stroop test as the primary task and target recognition as the secondary. So each participant has to complete 240 tasks, and because the first 2 repetitions are for practicing, so we excluded them in our results. So here you can see an encoder disk on the left side, and 3 stimulus types are different in their activated region. The static point lasts 500 milliseconds, and the short stroke has 2 stripes, and it will start exerting air jet on the starting position for 150 milliseconds, then moving for 350 milliseconds. And the long stroke has twice moving range of short stroke, so it lasts at 50 milliseconds. And the strokes on location 2 will reduce to a half because of the mounting position of IR sensor. So here are our study setup, and we use a keypad for the stroop test. And we attach a paper on our prototype to avoid users seeing the nozzle and stripes. So this video shows the practicing repetitions when doing stroop test and recognition in parallel. And participants have to maintain their accuracy of stroop test above 90%. And in this condition, we will show the answer and indicate correct position. And after the practicing, there will be no more hints about the answers. And in another conditions, no load, participants have to wait until the stimulus to come up and response. So here are the confusion matrices across 6 conditions. And you can see that location 2 and 3 were easier to get confused because of the contact region are closer to each other. On the contrary, locations 5, 6, and 7 were more accurate and easier to distinguish because the contact regions are tilted and separated. For the mean accuracy, we only found a significant mean effect on stimulus type, and the overall mean accuracy was 77.5%. And with the comparison, we found that long stroke was significantly higher than point, and long stroke with no cognitive load achieved our best case, 82.6%. And some subjective feedback from our participants, they preferred long stroke because it was clearer and easier to recognize, and they also reported it was difficult to concentrate when doing the stroop test in parallel. So here we compare our results to Tactile ring and thermal bracelet, which all have target recognition on X directions. So our work is slightly better than thermal bracelet and Tactile ring without pattern. This is because the target density of finger was denser, so that it was difficult to recognize. However, using pattern like virtual point can increase the recognition rate, and we believe motion pattern could also apply to skin stroke on the eye ring. And considering the modality between these three, the skin drag is subtle and invisible, and the co-stimuli is crisp and sharp. So our feedback have no physical tactile so that it can be applied to the vulnerable region and sensitive region. So now I will wrap it up. For the design implications, we suggest that using long stroke in the future application because it is easier to recognize, and avoid location 3 since it was perceived vaguer than others. And our system have an issue of turbulent airflow, and we believe this could also be a future utility. For example, like dual blink forces users to blink when using VR too long. And the user reported itchiness on our stimuli. Previous work showed itchiness can be applied to notification since it is sharp and cannot be avoided. This could be one of our future applications. Our work still has some limitations. For example, the end-to-end movement of the nozzle takes 6.5 seconds, and we believe this could be improved by more sensitive IR sensor or encoder system. And for a complete rotating range in the future prototype, we can change the mounting position of IR sensor and encoder disk to the outer edge of our prototype, like the implementation in Tactile ring. And for the future work, we could also explore sequential or simultaneous stimuli on iRing for multi-nozzle design. Also, we hope skin stroke could induce affective feedback in the future, like representing the tactile feedback of teardrops and sharing emotional feedback. So finally, I will conclude my talk with our contributions. Skin stroke display is a prototype inside an HMD that provides stroke haptic feedback on the iRing using motorized airjet. We demonstrate our applications and conduct 3 user studies to show our feedback are valid and recognizable. So thank you for watching our presentation video. I'm happy to take any questions. Feel free to leave any comments or contact me directly. I would also like to thank to my collaborators, Yizhen, Roshan, and Li Wei.